what we're going to do now is do a little question and answers from yesterday's presentations. I think what we'll do is, Dr. Marchetti, and let's get our group just to go up to our panel table, and then we can answer questions. May take a minute or two just to get organized here.
Maybe I might comment. I had yesterday some question about 1.1 millimeter. Why 1.1 millimeter? Because initially we tried everything between 0.5 millimeter, the formation of the center of the membrane, and 1.5 millimeter. 1.5 millimeter has a problem because the membrane, until it is flat, it forms very easily, and the delta A and delta B are very small. But then it increasingly becomes stiffer the more it is not longer flat. So 1.5 was too much. And on the other hand, the bigger the better, because when you want to measure something, it is easy to measure something. The error, everything becomes smaller. So 1 millimeter was a good compromise. So the idea was 1 millimeter. Then there was a change in some button between the central disk, and then came 1.1. So the intention was 1 millimeter, selected in this range between 0.5 and 1.5. And then for two reasons, some modification ended up with 1.1 millimeter. The idea was to have 1 millimeter.
Okay, I think one of the nice features with the DMT as opposed to the cone is the dual gauges, where you can read the low when you got low readings, and then you have the high. With a cone, you have just a set of strain gauges that has to go all the way up to the full load. So if you're trying to measure something in the very soft area, you're looking at the first 1% of your gauge, strain gauge, and you have some error there because you're just looking at the low end. The advantage of the DMT with the dual gauges is that you can read the low one when you're really in the low area, and you can read it very accurately to the nearest 0.01 bars. So just a comment if you want to add to it.
I suppose Ambin Huang has even used a lower gauge because you can replace the first gauge with one even more larger one, low scale. You can get any accuracy as you want because actually it depends on the accuracy of the gauge. Yes, the gauge is very important. You actually, when you take delta A and delta B, they cancel out. So we try anyway to have the zero of the gauge in the zero position. But even if it's not zero, well, we like to have it in zero. But if you measure delta A and delta B with the same gauge, they cancel out. Right. What is important is the zero, because many liquid soil, what you read, not the pressure meter. I would like to know more, because in the previous a few slides before, the one about arching, I said that the one about arching. No, this one. Yes. I emphasized the problem of arching with the conical probes, and so I would like to know if anybody has experience with the cone pressure meter, if what I suspect has some base, which means some problems due to arching in the cone pressure meter.
During my PhD research, I did some testing with cone pressure meter, which I developed myself. Its name is Newcastle Full Displacement Pressure Meter. There is a cone in front of the pressure meter. From that cone pressure meter, I determined the yield pressure, same as P0, and the yield pressure, same as P0, P1. The displacement pressure meter values are slightly higher than P1 and P0 because that pressure meter loads a larger volume of soil. So there is a correlation between marquette P0 and P1 values with the full displacement pressure meter values. I have I don't have the graphs here, but I did some comparison. So there is a comparison. There is a logical trend of variation.
And what about the rigidity of the membrane? Because of course a flat membrane deforms very easily, but a circular membrane either is made of rubber, but then becomes vulnerable, or if it is made of...
Yeah, that is expanded to a certain limit. Yield pressure of pressure meter is up to 100% cavity, cylindrical cavity expansion. So pressure at that stage is comparable with P0, P1.
Thank you.
Professor Marchetti, I had a question about the using the DMT for road compaction or for determination of modulus, that slide. In a standard California bearing ratio test in the field, the test is done with lead weights or something like that to provide a vertical stress. I wonder whether if you did the same thing with the DMT, whether you might get rid of the the low DMT readings at above the 250 or 25 centimetre depth. Presumably the first 25 centimetres of the test, the results are lower because of the fact that you don't have vertical stress. And the DMT is yielding the soil more easily. And I just wonder whether maybe this test could be more marketable, if you like, if you could use lead weights around the DMT the same way you do with the CBR test, a standard CBR test, and see whether that low part of the curve disappears.
The surface, yes, you cannot have more than Kp as a K value. So this is why at the top the modulus is cannot be very high. Now your question about the confining.
My problem is I think this is a fantastic idea. My problem is how almost every time you have to sell an idea like this on a project like this, you have to sell it to some authority that has a huge paradigm. They've been doing something the same way for decades. And I can see that it might be hard to argue that you can use this technique when the first 25 centimetres really you can't test so successfully. And I think it may be worth a little bit of research to try some lead weights and see if that gets rid of that problem.
But in fact, this was just an idea. It was just the beginning of something that somebody could be interested in developing, because it was a curiosity, was interesting, but by itself is not particularly useful. But it's a piece of information which is interesting and is a starting point.
I have a question on shear wave velocity measurements. When you have casing or hollow stem augers in the ground, I know I asked this question yesterday, I'm still not clear in my own mind why there's not an influence from that steel in the ground when you're taking shear wave velocity measurements with the surface.
About the casing?
The casing or
whatever. Incidentally, medusa means jellyfish, is the same thing. I don't know if you have this term in English. Medusa is a very seldom used. It's like jellyfish, not octopus, but and the idea is the membrane will fluctuate continuously. That's why it was called the jelly medusa. But apart from that, your question was about the casing. The measurements are taken outside the casing. From the bottom of the hole, you always go deeper, and you measure in the virgin soil what you have to measure. So the casing cannot have any influence because you are lower outside the bottom of the hole.
so the shear wave induced into the steel augers or casing won't influence those readings at all?
No, because probably something will arrive before And these are probably these tremors that you get before the big spike, because what you are really interested in just this big spike. And this has been used before us by so many people, and we have at least two reasons to think that this can only be the shear wave. First of all, is the order of magnitude of the value, because when you have 100 meters per second, 2 meters per second, it cannot be in the steel, which is much higher. So the two things are very well separated. And then comparison with SASV and other methods, which certainly are independent, so cannot be affected by the same problem of the casing, indicated that this is the shear wave. But in particular the values, because when you have a value of 80, 10, 100 meters per second, this can only be the shear wave.
I don't know, the gentleman that talked about Medusa, is that the right term that he used yesterday? Is that, I don't know whether it's appropriate, but is that just using like a wireline equipment for rock coring adapted to soils? Is that?
Yeah. Yes, to answer the question, it's correct. It has been used rock coring equipment adapted to soil. Okay, and the same equipment is used to drill soil, to drill rock, but changing the core barrel to make CPTU tests and to make the Medusa test, the dilatometric test. But to avoid any misunderstanding, I would like to point out that Medusa is not a seismodilatometer. It's only a dilatometer, because the seismodilatometer, as far as I know, needs a cable coming up to the surface. So it's only a dilatometer.
Right, only dilatometer.
Only dilatometer.
And it's, that technique has been adapted to use like polymers or drilling mud, different
Yes,
than,
yes,
okay,
yes,
for
absolutely.
soil coring where you get an actual,
yes, yes.
and the sampling of the soil itself is what type of, you
That
were
I
indicating-
use normally for shallow depth. I use modified Osterberg sampling, and for greater depth I use or Denison or Shelby tube for sampling.
that you over drill.
Yes, yes.
Okay, thank you.
Welcome.
I think Dick's question with the casing was, why doesn't the wave just travel down over to the casing, then down the casing, and then to the geophones? But I think the answer, maybe you can answer it, but is that you really have two geophones at different intervals, and you're just measuring one and the next, and you're kind of comparing the two to get your delta time. And I think his question was more like, what's the effect of the casing, and how does that affect your answers? If you can answer that a little bit more.
Was the question? What? But we,
The same question applies to the cone, of course. When we put the seismic in a cone and you hit at the surface, why doesn't the wave travel down the rods? It does. It does, certainly it does. But the magnitude is not there, okay? It's a refracted energy. So, and you're making a differential measurement. That has totally nothing to do with steel anywhere, right? So, and what's the wave speed in steel? 16,800 feet per second. And,
Yes, I
and
think
how
that-
many soils have a wave speed of 16,800 feet per second? Ignore that, okay?
yes, they are completely separated.
If you get 16,800, it's just not soil.
We had an experience in which, I think by error, the tool, the probe, the seismic TMT was inside the casing, and in this case we had terrible waves. And as soon as the thing went below the bottom of the hole, the waves became normal.
Can I try to add something to the discussion about why the waves does not travel in the bar? And a reasonable explanation can be that simply the bar is very much more stiffer than the surrounding ground. So there is a high contrast of impedance, and almost no energy goes into the bar. So compared to the energy that is traveling in the ground, there is almost no energy in the bar. So the wave that is traveling in the bar is so low energy that does not arrive to the position of the geophones. So the bar is not moving for that reason, in my opinion.
Can you explain how this really works? I guess you just push it down to a certain level and just wait on time. How does your communication work between your laptop and what's going on down in the hole?
There is no communication. Excuse me. There is no communication between laptop and Medusa while the Medusa is working, is expanding the membrane. The reason why the laptop is connected to the Medusa prior to start the drilling operation, the testing operation, excuse me, is that the laptop programs is setting the Medusa expansion time and so on, and the laptop simply shows the operator how the Medusa is moving. It is like a film on the laptop showing what is happening underground. But the laptop, while the Medusa is working underground, there is no communication between the laptop and the Medusa.
So do you just push like down to your test depth and
Yes.
wait a minute or two
Yes, yes.
to make sure it's
Yes.
taking the readings?
Yes.
And then after that elapsed times, then you know to push again to the next step?
Yes.
Is that how it works?
Yes. It is how it works.
One thing wasn't really clear, but I think I understood it, was when you're doing your Medusa, you're coring down, say, your 100 meters, and
Mhm.
then you pull it back a meter and a half, and then you have your DMT blade sticking out a meter and a half, so
Yes.
that when you push back, you don't have all the resistance of your casing, because it's really just going down an
Yes.
open hole, and you're really just pushing the blade
Yes.
for your thrust.
Yes.
And you can't really push any further than what you retracted it, otherwise you'll be trying to push all your,
Yes.
your
Correct.
coring.
Correct. And the length of the pushing is proportional to the stiffness of the soil. I mean, if I had very soft soil, I could add 1.5 meters rod. So to push 3 meters instead of 1.5 meters. I think that 3 meters could be the limit, not due to the penetrability of the soil, but due for operational matters. I should add on the surface so many casing rods as many pieces of rod I've added to the Medusa. So it's not sometimes so easy.
The bits that you're using to cut the casing in, is that like a bottom discharge bit? I mean, you don't get sample disturbance because you're pushing a lot further down?
No. I can use several methods of drilling. I can use no coring, like a tricone, wireline tricone inside the casing. I can use continuous coring. I can use also sampling if I want. But the bottom of the hole normally is not so much disturbed. Let's say 20 centimeters of disturbance normally.
Well, a roller cone or bit like that is independent of the casing, right? So the production that you were wanting was for deeper holes using the wireline technique.
Yes.
So using a roller can and those kinds of things are using rods. Is that not
Yeah,
correct?
no. I never use rods. In case of no coring, I use a wireline tool. I have some photo I can show you later.
Oh, okay.
It's
yeah.
a tricone inside, which is inserted into a core barrel inside the casing.
So it
and-
locks in place.
Yes.
Okay. Thank you.
I guess one of the questions is, we saw how well the seismic DMT worked yesterday, and I saw it Friday as well. I'm sure everybody has the same question. How much does it cost?
The first one has been will be delivered in April to the Zurich Polytechnic, and the cost of 2 blades with all the rest is 19,000 euro.
This is a kind of Dorothy Dix question because I asked the question yesterday and you answered me. But I think a lot of other people might have been interested in the question and the answer. One of the things I really like about the DMT is it's very, very robust compared to a CPT. I run a small contracting business and we break CPTs and we're always afraid of them, but we're never afraid of breaking the DMT. And the question I asked yesterday was whether the seismic DMT is just as robust as just the DMT, and I know the answer, but maybe you'd like to give that answer again.
Well, the answer is that 2 years ago we already had SDMT with several cables and some complications, and much of the effort in this recent last 2 years was to make it as simple and as robust as DMT, so could work against the operator. I always assume the operator is against me, the operator in the field, to start with. So the effort was not so much in changing the principle, but in absorbing all the possible things that could go wrong. So I'm acutely aware, as all of you, that what is important is there cannot be complications in the field. So the philosophy was exactly the same as with the mechanical DMT. Of course, it's a little more complicated, but everything was tried to be absorbed inside the instrument. So outside, you cannot have not a physical possibility of doing damage.
Sorry, Diego. The software that's been developed, you got a graph that depicts your material index. You got sand, your clays, and your silts. Is there a particular reason that the software only classifies those 3 materials? Can you go further right and look at more granular materials? Or does one just assume if you're above an index 5 and above that you are in granular materials?
Well, the fact is, when you go from to increasing the grain size from clay to silt and from silt to sand, you have an ID increase. Then, actually, when you have gravel, you have a very low P0 and becomes not very well measurable. So, and also the has no sense, has no meaning. What you get in if the particles are too big. So there was no point in going beyond ID equal to 5, 10, I don't remember, 10. I don't know if this more or less answers your question, because it was since I didn't show the origin of this ID, but the fact is, if you go to the site immediately, you see that when you are in, I don't want to know the reason, but when you are in sand, the 2 readings are distant. When you are in clay, they are close. I don't want to go into the reasons why, but every operator says, "Oh, we are in sand," because immediately he gets familiar with this fact that. So ID is like a vicinity index. How near are the readings means clay. If they are far, it is sand. And if you have a sand which is more sandy than the sand, it becomes a gravel. Gravel has no meaning, so we stopped at 10.
I want to add that the problem is when the size of the grains is quite large and not small enough compared to the size of the membrane. So what happens is exactly this, that you get a very low P0 and a very high P1. And of course, you get a high ID, but it's just non-significant. So it's gravel.
Someone showed a correlation yesterday with surface wave technology, geophysical, relative to shear wave velocities. Does anyone have any comments on surface wave geophysical techniques for shear wave velocity determination, out of curiosity?
Personally, the only experience I have is the comparison between what other people have given to me as a profile obtained in different ways, and we have compared this with what we got, but I'm not very familiar with the other techniques except for this. But maybe somebody has.
An expert?
I'm expert on food and restaurants.
Oh, okay.
And I am very proud of
Okay, good.
The use of spectral analysis of seismic waves is giving you a similar, although less precise information as cross-hole seismic dilatometer, which is a downhole technique, and so on. The use of spectral analysis of seismic waves is mostly related to the problem of the source energizing the ground surface, and if the soil profile is normally dispersive or inversely dispersive. Normally that means that the stiffness is more or less constant or decreasing with depth. And this is the case where the SAS is working very well. When you have the abrupt change in stiffness, for example, you have soft layer of very hard soil or rock, this is becoming a problem. Who is really expert on this specific issue is Dr. Foti, which is also here from my university. I would like only to say that in many places, including the location of the Messina suspension bridge, we did SASF and cross-hole, obtaining extremely good comparison. For the Messina Strait Bridge, we were able to determine shear wave velocity from SASF down to 80 meters depth, obviously having very large energizer of the ground surface. And the results are completely fitting the results of cross-hole. I have on my USB key these results, but it will take some time to show. I believe that Dr. Foti can add something more.
Yes, I can say something about our experience. We have been running SASW test in the last 6-7 years, several of them. And from our experience, the comparison with cross-hole and downhole test, and also with seismic cone test, has always been very, very good. I mean, there is a good comparison. The results are absolutely comparable. As far as there is a main aspect to be clarified, is that obviously, as Professor Jamelkowski was saying, the resolution of the test is not the same, and because if you think that surface wave tests are performed only from the ground surface, so as a matter of fact, you cannot expect to have the same resolution with depth as you have when you are inserting your sensors inside the soil. So obviously, when you are using cross-hole test or downhole test, you are putting your sensor inside the soil. You can expect to have a high resolution, so to resolve very thin layers also at depth. The resolution of SASW decreases with depth. So you have an high resolution in the shallow part of the soil, and then the resolution becomes less and less because, as a matter of fact, your sensors are all on the ground surface. So you should expect something like this. And the other point is that there is, is not the fact that the soil is not increasing stiffness, only increasing stiffness that. So if the soil is not normally dispersive, as Professor Yamarkowski was saying, it's not that the technique cannot work. The thing is that the measurements are much more difficult to interpret, but they can be interpreted anyway. So in soils in which the stiffness is always increasing with depth, or the variation of stiffness are not very marked, the interpretation of the test can be much more straightforward than if you go to a more complex site with various change of stiffness, so higher stiffness, lower stiffness, and so on. I don't know if this was a contribution to the question. If you have other question, I can answer it.
This is the results of comparison between a cross-hole test performed down to 100 meters depth. Here is shown only to 80 meters. They are the pink dots, okay? The yellow line is representing the results of spectral analysis of seismic wave done in this soil. The soil profile is mostly gravelly sand, okay? And you see there is a perfect fit. We have many of such results. Dr. Foti did similar test in Pisa, close to the Pisa, Leaning Tower of Pisa, finding also very good agreement. Therefore, as he mentioned, obviously there is some difference in definition of the shear wave velocity, but substantially cross-hole is very expensive, and the spectral analysis of seismic wave, if properly done and properly interpreted, is much cheaper. Sorry.
Yeah, I was waiting for everyone to have their technical questions because my question is more about maintenance of the DMT. Our firm is in Canada, and we primarily use the DMT for saturated clays, which are sort of act as blankets over glacial till materials. And our experience is that for every, say, 4 hours of use of the DMT, we spend about 2 hours on maintenance on the equipment. So I just wanted to find out if there's people with similar experiences, or maybe we're doing something wrong at our end. Well, we frequently change the membrane, and our guys think that sometimes when water get inside, it affects our readings, so they have to open it up and dry out and take out even that perspex cylinder in there too as well. So I'm just wanting to see if there are similar experiences.
Do you hit a lot of gravel, or what are you encountering to cause problems to your blade?
Well, not the blade itself, because the blade is okay, but it's just, sometimes they're out there doing the readings and you get the constant beep, the buzzer is on constantly. So they think maybe it's like water or so forth penetrating the membrane. So they have to disassemble the stuff, dry it out, and then start again. So
I guess what I do is you can tighten it down quite a bit, and you can pressurize it and, at the surface, and put it under water and see if any bubbles are coming out, and then fix that spot if you have a leak there.
Yep.
Yeah, I run a small consulting business with a small contracting arm that does quite a bit of dilatometer testing in Australia, and we've had the exact opposite experience. It's only really recently, working at very high pressures in very dense, sharp sand, that we've even had reason to think about maintenance being an issue, because in one day we broke 2 membranes. But prior to that, we've had almost no maintenance issues at all.
I think you have problems only when the membrane breaks, because if the membrane doesn't break, the leakage should not be any leakage, because as was said by Roger, you try before, and once there are no bubbles, you never have a leakage. If you break the membrane, you have leakage. I think one of the improvements that we want to do now is the third step with the membranes. What I mean by third step is I remember 15 years ago we had the membranes which were much softer and vulnerable. These present membranes are much stronger, but people of course want to go to stiffer soil, to gravel, to go through gravel, and then I think it's a good time for us to try to obtain membranes which are even stronger, because this is the only point that requires maintenance, and of course maintenance is something we don't want to do, because in addition to changing the membrane, sometimes you have to clean, and this takes time, and a special person you cannot do by anybody. So if the membrane becomes stronger, I think is an important benefit. So this is a high priority for us.
I'd just like to say something about penetrating gravel. I mean, yesterday we saw with a drill rig, what we could do is, you hit gravel, you just auger through it and continue on with your hole. What we didn't see yesterday was that same gravel layers there, and we still had the push rigs, and we had to, we hit the same gravel, but we have a blade that we use that's worn out, and we just doesn't have a membrane on. We just push that through the gravel to pilot a hole, and then put the regular instrumented blade down and follow the same hole, and then get down below it, and that seems to work pretty well, at least at not tearing your membrane getting through an obstacle.
There are several bodies in the world that develop standards, and ASTM is one of them. In 1980 something, I've forgotten how long ago it was, Dr. Schmertman published a proposed practice for the dilatometer as a first step towards an ASTM standard. And eventually, sometime around 2001, it was actually approved by ASTM. ASTM, and many of you have probably seen it, ASTM has a policy that every 5 years they revise and make changes to any standard, and that's a required policy. It's not an option. So 2001, this is 2006, and 5 years is here. If any of you are users that have used the standard, if you've never seen the standard, you should probably take a look at it. And if you have used it and have found problems using it, we would like to know. I'm a sub chairman of something or other that puts me in charge of making changes. And so I'm very interested to know if you have any recommendations, and that includes Dr. Marchetti. You can either contact me or Dr. Marchetti or Dr. Kraps at GPE, and with any changes that you might have. It's available online. All the ASTM standards are available online. It just takes money. Actually, it's fairly cheap to just get one standard, but like I said, you contact Dr. Marchetti through his website, or Dr. Kraps through the gpe.org website, or me at pbullock at pile.com. So, if you have any comments, we'd like to know.
There was a very good and very promising presentation from Paula about the use of KD to evaluate the liquefaction potential. And some comments or parallel comments related to the use of V sub S, the shear wave velocity. I believe that there are some number of statements which can clarify the frame of both approaches. And the common frame is that both Vs, shear wave velocity, and no matter how polarized, and the Kd, they're essentially representing the state parameter. The state parameter, which was initially embodied in the critical state soil mechanics and thereafter was clearly formulated by a paper in geotechnique in '86 by Bean and Jeffries. The state parameter is especially suitable to define the state of coarse-grained soil, sand, gravel, maybe silty sand if the silt fraction is not plastic or of high plasticity. The state parameter is combination of two things: the void ratio or porosity and the effective stress state. And this is very useful in study the behavior of coarse-grained soil, because practically is giving you the measure of to what extent the soil is contractive or dilative, which is the essential issue in the undrained behavior of sand. And this is for sure because the shear wave velocity is by definition function of void ratio and stress state, and the Kd, we have a very large amount of data from the calibration chamber test, which has have never been published, but obviously the boss knows everything about, is also very well correlated to the state parameter. Now, what are the difference? The differences are the following. The shear wave velocity is state parameter dependent and is very sensitive to have even very small bonding between grains, which are immediately reflected in the velocity of wave propagation. Kd is equally sensitive or even more sensitive to state parameter, but is during the penetration, it is partially erasing the effect of bonding or aging. We don't know. We are not able to quantify this. Obviously, what's happened when you apply these two methods to liquefaction? The shear wave velocity probably is giving you a non-conservative answer if the earthquake event is enough strong to break, to erase the bonding effect of aging, any very small structural effect. Why Kd, we don't know to what extent, not certainly only to partially erases this effect. Therefore, probably the question is not to have a fight of V sub S against Kd, but use the bot method and have a look at what is the earthquake intensity and to make the engineering judgment. This is the first statement. The second statement is more general. In last 20-25 years, we moved from SAPT to CPT, CPTU, shear wave velocity, DMT, trying to evaluate free field liquefaction using so-called simplified method. I am not a great fan of SAPT because it is a very rough test, but in order to be fair, one must remember that majority of the database related to the liquefied site all around the world are still linked to SAPT results, and that the many correlation given in the literature is based on some translation of QC or other in-situ tests to SCPT. And this is clearly the weakness of the new method, which are in principle more powerful and more rational, but are still lacking the sufficient database. Mostly lacking the test before seismic event, therefore before liquefaction. In any case, even there is no liquefaction, we like to have the data before seismic event. And I believe that this is the present situation. We must go ahead with this new method because they will be certainly much more reliable, but we must try to collect more database. I would like to end with the one point which is very important. No matter how we shall refine our simplified method to evaluate the liquefaction, we must remember that this is a free field method, and we are interested in liquefaction under existing foundation. And I have no time now to make the comments, but for example, for the Messina Strait Bridge, where we have enormous foundation, this is 3.3 kilometer span suspension bridge, the old method of evaluating the liquefaction resistance of sandy gravel or gravelly sand were giving you liquefaction to the depth of about 25 meters. Once we made a more advanced analysis, putting the foundation on the soil and making one-dimensional coupled liquefaction analysis, the problem almost completely disappeared. Therefore, all these simplified methods are generally suitable for not very heavy earthquakes and are conservative. At the Messina site, the earthquake is 7.1, 7.2, very strong earthquake. Thank you.